Welcome to part 12 of the power supply project. When I originally set out the design, I tried to think about the format, and the original plan was to have a format that's not too dissimilar to this sort of final prototype. It's sort of a L-shaped form factor, and the idea being that you could mount this to a heatsink that way, and it will keep the module nice and self-contained. You could pretty much use any kind of heatsink just by having, you know, some say a bolting, some kind of simple fixing, either a couple of screws or whatever. So that was the original plan. However, having thought about that quite a lot, and before I committed the final PCB, you know, cost is still important when you're doing these sorts of things. And obviously, when in terms of manufacturing, if you're trying to make these things, especially in low volume, things like this, you really don't want to be making specialist parts or trying to buy specialist parts, and unless you're fortunate enough to have some of these laying around, or pick up in your pick up in a boot sale or something like this, then you know that can be quite difficult. You know, you want to be with this kind of power supply, this kind of high power electronics, you also want to be able to force air cool it. And so I gave some thought to how I could do that, or how I could create a form factor that would allow anyone to do that, and you know, using perhaps simple, easy, accessible, off-the-shelf components. So the idea I came up with was a slightly different form factor. So assuming this is representing the final PCB or some variation of it, the idea would be to have a flat plate of metal like this, flat plate of aluminium, mounting the power components on it with the legs bent upwards. So for example, let me just grab an example. So something like that. So those would be fixed to the PCB, to the back plate, and then the board would mount on top of that. Now the reason for doing that and making that flat, so you might think, well, that's going to be more awkward to mount like that, and the thinking was actually not to do that, but to take advantage of something you can buy off the shelf for about $5, which is one of these. Now this is a CPU cooler fan. This is for an AM2 socket. It's very, very off the shelf, available. You get the heat sink, you get the fan, it's all pre-wired, ready to go. Generally you can get them either flat like this or with a copper thermal coupling. And the idea is that once you've got the board mounted with the components this way, you can mount the fan on top this way, plug that into the controller board, and it solves a number of problems. First of all, it's still quite compact. It's very compact. If you're mounting that inside an enclosure, you can simply mount that on the base. You can mount 3 or 4 of them next to each other. You've got forced air cooling around the actual core power devices, and then you can use, you know, just air distribution or air movement inside the enclosure to take the heat away. So that, I thought, you know, that would be a good easy to use form factor. Getting plate aluminium like this cut to size really isn't that expensive, perhaps a couple of dollars a piece, $1.50. As I say, these are $5 to $10. You can buy them for on eBay or your local computer shop. You know, they're very, very, very accessible, and there's all sorts of variants of them. And the only challenge really is to make up a bracket to hold the fan still. There would be no point in using something standard like this if you couldn't make up a mechanism to allow you to use the standard fixings just to clamp that down. The way this works is just tension based. So if there's a couple of posts that these squares can hook into, set to the right height, you simply clip those in, throw over this tensioner, and that holds the thing all tight together. So that's the form factor that I've decided to go with for this. And on the back of that, I have designed a PCB, which I've now got back. So here's the PCB. Now, because again, I wanted to keep everything completely self-contained. The PCB has ended up a little bit bigger than perhaps I intended it, although not too much. Now, the main thing to note is that the size of the plate is actually smaller than the size of the actual PCB, and there's a very good reason for that. So on the PCB I've got 4 mounting holes which will be used to fix to the plate, 2 additional mounting holes. The intention is that in an enclosure this would mount either, you know, onto whichever surface you mount it onto, it'll be component side down, so there'll be some standoffs here to mount, and on the top here would be the fan. And then because the other components which were bulky were the bulk capacitors, so there'd be two of those there. The fan will connect to the board, and that'll be the basic form factor. So that's kind of you know, how I decided to take the design forward. That is the form factor as it currently stands now. So that's the plan. Now, in order to do that, obviously this has to be drilled and made, and I have I'm going to do that next. That's my next job. But basically, I've used the PCB program to dimension and lay out the components. So there's five components that are fixed to the plate. You've got the bridge rectifier. I've done that simply because of the potentially high current handling of the module in its low voltage mode. The high voltage LM317 regulator that takes the supply and regulates it down for the control circuitry. I've put output protection diode, which is a dual diode here, and that's obviously mounted because that will dissipate some heat at high current levels. And if you recall in the last blog post, I talked about having a pair of output devices instead of one. Now that's optional. You can put one or two in. For the cost of them, my feeling is just put both in, regardless of what you're doing, just because at the very least, from a thermal management point of view, it distributes the power dissipation across 2 devices instead of 1, which has to be better for reliability. So that's next. I've got to get out into the garage and get some tools and start working on that. I have built the very first board. So here it is. All the components complete. I haven't put any power components on there. I have powered it up and I have programmed it because I changed the microcontroller. I did have to change some of the code, but I have now programmed that. And unlike the original design, you can see the microcontroller was quite a lot smaller. The original microcontroller, I'm using 3 PWM outputs now. One to control the fan, so PWM to manage the speed of the fan. This is a standard 4-wire Intel fan, by the way, so you know you've got 0 volts, 12 volts, tacho out, so you can monitor the speed of the fan, and control in, which is a PWM signal, 25 kilohertz PWM signal to vary the speed of the fan. So quite simple. So a PWM to drive the fan, a PWM circuit to generate the negative supply, which is this circuitry around here, and a PWM signal to control the trimming of the front end op amp, which I talked about in the last blog. So that's all now programmed up and working. I've verified that's working as far as I can tell. So the next thing now is to construct this, put all the power components on, and start doing some testing on it. So that's the next thing to do. Okay, I'm going to go and do that, and once I've built the initial physical construction, I'll come back and show you what that looks like. Okay, see you in a minute. Okay, so I thought I'd do a quick video on drilling. I'm sure that everyone knows how to do this, but anyway, I thought I'd show you how I do it, which is a very standard way. The aim here is I've got 8 holes. They're all going to be M3, so 3mm metric thread threaded screws. So I need to drill and tap them. So you need a couple of things in order to do that. First of all, you need a drill bit of a specific size. You should check that. I think it's about 2.6mm or something. I can't remember the exact size, but it's specifically for an M3 tap. You need an M3 tap. So that's a thread cutter. I'm not sure how. Very, very simple thread cutter. You need some oil. In fact, I'll probably use some bit of beeswax, just for lubrication. Maybe not actually beeswax, is probably not good here, but yeah, a little bit of 3-in-1 oil, which I've got lying around here somewhere. And most importantly, a centre punch. And the reason why you need a centre punch is you know, the drill will drift if you don't make sure it's correctly lined up. And I'm going to do this by hand, so I'm not going to fix the. I'm going to hold the aluminium by hand as I drill it, and therefore getting a good center point is really important to make sure the drill registers and you're able to align it by feel. So I'm just going to do that now and drill the first holes, and I'll come back in a minute. The accuracy of when you punch the holes will dictate, you know, the accuracy of where you position the holes on the final piece of work. So it's worth taking your time at this bit and get that as close as you can get it. Okay, one of them are slightly off, and you can correct this. It's just a case of obviously don't make them too big. Just go in at the opposite angle, and you can generally correct these. Okay. All right. Now at this point I'm going to remove the template, because it'll only be in the way now. I've got the suitable locators on the metal itself. Okay, so this is what you end up left with. I don't know how well that'll come up on camera, but you can see the registration punch marks there. Okay, it's just... I can't find my 3-in-1, so I've got some white spirit to hand. I think that'll do. It's just the main objective here is to keep the drill bit cool, just so the drill starts a little bit slow. Sorry about the noise. It's just I've got it's actually a three-phase motor, and I've got a simple static converter. I'll talk about that some other time. But anyway, it's once it's going, it's pretty okay. So what I'm doing here is I'm just letting the drill bit find the location based on, and now I've found it, I'll hold the workpiece still and then just drill the hole. I've just repositioned the camera there just so, because my hand was in the way, I noticed, so just give it a different angle just so you can see. Okay, so that's the 8 holes drilled. Nice and straightforward. I'll tap one and then I'll stop the recording just to. There's no point in you watching me repeat myself. Keep it well lubricated and as straight as you can. By hand, it's always difficult to get it perfect, but the drilled hole, using a good pillar drill does help because it keeps the holes straight and true, and that does ultimately guide the tap. So normally about 1 turn forward, half a turn back, just to let the swarf break out. Again, if it gets sticky, just keep it lubricated. Saves the tap. Means you get more life out of it. So there you go. I think that's tapped nicely. I generally run it in a fair bit of the way and then bring it out. I also let the tap come out on the weight of the tap, so put as little weight or pressure on it as possible, just to keep the quality of the threads reasonable. Okay, so that's tapped. The one other thing you have to do is just deburr the edge. Let me just get a drill bit for this, sort of 6, 7 mil, something like that. Very gently by hand. You want what looks like a very small countersink, but most importantly you want it feel it smooth to the touch when you rub your finger over it. Okay, I'll come back. Actually, I've just realised I've actually missed a hole as I was just counting in there. There's one there. Anyway, so I'll go finish that up and I'll come back and we'll start the construction. Okay, so after some drilling and messing about, there you go. That's the drilled plate. To mount the fan using the existing brackets, I've made a pretty simple riser. I need to clean these up. They've still got a permanent marker on there from where I was marking. Basically, a riser which small piece of aluminium bar. It's drilled and tapped, so I can screw through the base plate. Countersunk, so interference locking once they're tight. That obviously holds the riser in place. And then a simple threaded hole here holds that in place. So when we mount the fan, okay. So if I just I'll just put this together and show you it lock in place. I ain't got the camera down. Where is it? it's quite tricky getting the right height and the right width. I'm not exactly perfect, but it's certainly good enough to for the first prototype. And of course, now having done this, I can take some more accurate measurements with the fan in place. It's pretty difficult to measure this. You know, it's to be precise, and also I found that this fan, which is also designed for the same socket, has a narrower gap here than this one. So I guess this one is designed to perhaps angle in a little bit more. Anyway, it's close enough and does the job. Let me just tighten these up. So I will put some heatsink compound. I'm going to take this apart again and clean it up. Just take the engineer's blue there, the permanent marker off. But just for the purpose of doing this video, just show you that go together. So a washer and a screw. These are M4s, so I've used a slightly bigger screw here. Okay, so with those in place, just line up the fan over with the lock, and there we go. Nice physical construction, good thermal coupling. So when that's built, that'll be the construction. Okay, these are standard M3 spacers, male on one end, female on the other end. So those will go into the 4 corners here. The various components will mount on the plate here. Board will sit there. Okay, so same sort of spacers, slightly bigger. They're standoffs just to accommodate the height of this these connectors. Obviously there'll be lock washers and things of that nature here. Well, I'm slightly out here. I'll have to sort that. Okay, slightly out on the tolerances there. I probably should have used larger mounting holes. But anyway, you get the idea. That's what the construction is going to look like. Okay, there you have it. Let's that will come around here and plug into a connector right here. As you can see, 2 capacitors on here, and that will be the finished module. We'll see with the standoffs. Okay, so I'm going to go away and build that now. Clean it all up, build it, put the power components on, and next up I'll be powering it up and testing it. Okay, all the metal work is done now. That's the I just thought before I solder it together, I just thought I'd show you the power devices mounted. So that's the one of the regulators, bridge rectifier, pair of output devices. The circuit is designed to include a protection diode, which I actually don't have. I haven't got anything to put in, so I'm going to link it out for now. Just for the purpose of testing it, I'll fit it later. It's output and reverse input protection protection. So that's what it's for. So linking out will be fine. I thought I'd just also show you this when I inputting the output protection to to protect from reverse polarity, really there has to be a way of dealing with, you know, not actually, you know, no matter how good the diode is, if you put a car battery or some high current source, reverse polarity, you're gonna damage something. So I thought I'd fit a fuse, and this is the fuse. It's an 8 amp fuse. This will be the low power, the low voltage, high current model. It's an 8 amp surface mount fuse. It's a little, I don't know how well you can see that, but it's a little cartridge fuse that can be removed and replaced without desoldering, which is always a good thing. But the way I've done the footprint on the PCB is I actually included through holes as well. Now, there's 2 reasons for that. The first reason is in soldering this by hand, it's not going to be easy to get to the pads underneath, but by tacking it and then soldering through from the bottom, it should make life easier to actually get a good fixing on that. The second reason is in the construction, you may choose not to have the fuse on board here, but put it on the back panel or somewhere on the actual on the enclosure, the final enclosure. In which case, you can just put a couple of wires and take that off to the fuse holder. Anyway, I thought I'd show you that. Right, I'm going to do the final construction now, solder it together, and then the next thing is to power it up and test it. Okay, everything's built, mounted, soldered in. Now I'm going to give it a go and power it up. Just for convenience, I'll use a bench supply here to power it up. I'll just dial it up to 12 volts, and so I guess what I'm expecting to happen is the status light should run as normal. I'm going to put this on the AC side of the rectifier. It won't matter. It'll just verify that everything is around the right way and in the right polarity. I just want to do a basic power up test just to make sure that nothing fails. The status light should come on. The fan should run. The default mode that the microcontroller, the PWM mode, is at the fan's lowest speed, so it should power up with the lowest speed. I'm going to dial up 14 volts. I'm going to set the current limit to 500 mils just in case. Okay, and I'm going to power it up. Okay, so we got some status lights, and the power supply, the fan is running nice and slowly. Okay, great. So just make sure that it's drawing about, in that condition, it's drawing about 78 milliamps. So really very, very little standby current. 78 milliamps is very low. All right, next thing to do, I'm going to set it back up on my other bench where I've got the dummy load and the various meters and stuff ready, so I can do some tests and verify that it's actually delivering output and doing all the things it used to do in its prototype form. See you in a minute. Okay, so I've done some testing. Unfortunately, there was a bit of a problem actually with PCB routing, which is highly annoying, but not surprising. I think the last few hours I spent on it, it was quite late into the night. Anyway, so all the nets routed correctly. However, I'd forgotten everything I'd learned in the prototyping stage, and this ground point needed to be grounded at my star earth point, which, if you recall from the previous blog, was right down on the non-hot side of the current shunt, the low side current shunt resistor. Now, the way that the way the track's routed, or the net's routed, there's actually a 0 volt rail here, and I had a 0 ohm resistor just terminating there. And what should have happened is that should have been down here, terminating on this strap, on this track here, or actually at this point, if possible. Second of all, the same was true for the negative side of the remote sense. So there's a second bodge wire there, unfortunately, to get that work. Now, what difference that makes actually is fairly trivial. It means that there's at 0 volts out, there's an offset of about one millivolt or something. Anyway, I wanted to do better than that, so you can see in the background there, it's currently switched off and set to 0. and you can see that's the output, that's measuring the output, so it's minus 0.004 millivolts. So that's pretty off, and if I just turn it on, I've got it currently set to 2 volts driving into a load. So there's it driving into the halogen bulbs there, delivering 2 volts. Anyway, so that's unfortunate. There were a couple of other mechanical issues on the board. You would have seen earlier on when I was constructing it. The tolerances on these holes, these 3mm holes, I made the silly mistake of making those holes 3mm. They should have been a bit bigger, so I'm going to make them 4. There was also another error where this capacitor here, which is currently a 0.1, it should have been a 47 mic electrolytic. Electrically, it doesn't seem to have impacted the circuit, to be honest with you, so I could leave it like that, but I'll change it because that's how I've done the original testing. Anyway, so there's a few minor errors on the board that have caused me to have to bodge it up a tiny little bit, but other than that, it's absolutely working exactly as it was. So that does mean to say I had 8 boards made, and it means that I need to build at least one more prototype for the high voltage version of this, which I'll do on these boards, of course, and I'll learn in case there's any other issues, and then I'll get a final set of boards made. Anyway, so that's that. So I just wanted to talk to you briefly about the thermal management. I guess that's the first thing I tackled when I put it together in the way that it's currently put together. Just one other thing, I made a decision to move to 2mm pitch spacing connectors, which are not standard, but the 2.54mm connectors were just too big, and they, I could, if they were vertical, then I'd need risers would be too high. If they were horizontal, it was just in the way. So anyway, I've moved to much more smaller, manageable, standard JST connectors. They're 2mm. You can get these cables, these plugs and cables off of eBay for not very much money at all. You can see how I've made a programming cable. I simply take one of these, soldered it to the back of this little adapter board, which I think is an Olimex adapter board. There you go. Yeah, so that's that. Same with the serial interface. I've just soldered 5 wires to the back of the serial interface and made a small cable for that. So that was the other mechanical thing. Okay, so just talk about the thermal management. As I mentioned before, I'm using a standard 4-wire Intel fan. It's connected here. I've got a scope probe, which I'll show you in a second, on the PWM control line of the fan. The power supply is currently sitting here into a load, but not switched on. So it's running at room temperature. The temperature of the heatsink here now is sitting at about 25 degrees, 24.5 degrees C. And I've implemented the software inside the firmware to really deal with thermal management in a really simple and rudimentary way. I've taken the view that anything below 26 degrees the fan can idle, and then it raises the percentage of the fan from 0% to 100% by 1% by 0.5% every degree centigrade. So that'll take it from 25 degrees roughly up to 50 degrees centigrade. Anything higher than that, and the fan will be running flat out. I'm going to just do a test and show you that in action. For those of you who don't know, the PWM control on this fan is really straightforward. It's meant to, the ideal spec, they say, is run it at 25 kilohertz and a variable mark space ratio. So if you put a 0 volt signal on it, it'll run at the lowest speed. If you put a if you put a 0 volt signal or no positive, it will run at lowest speed. If you put plus 3 or 4 volts, I think it all needs to be 3 or 4 volts. So permanently on, full mark, then it will run at full speed. So that's, and obviously the variation between that will give you variable speed. So what I'm going to do, I'll speed this up because you won't want to sit here and watch this do this, but let me just zoom out and show you, get some more of this into view here. Okay, I will show you. I'll do a separate thing on the software here because I've changed the software and I can see the fan speed. I can see the power that's being dissipated into the regulator. I can see the power that's being dissipated into the load, and I've got other parameters to look at the temperature monitor and the fan RPMs and stuff like that. So what I'm going to do now is I'm going to drive it into a load, which will raise the temperature. I'm going to set this at 4 volts, 6 amps. I'm going to turn the output on. So you can see that the bulbs here are lighting. These are my very rudimentary output load. And you can see that the temperature started to raise now. And if you watch this mark space ratio, that's currently the minimum. And you'll see now as the temperature rises, that will start to expand out. I'll measure the time elapsed because I'm going to speed it up when I edit this down, so you don't have to sit there and watch it, and I'll let you know how long it takes to get to 100%, which will be 50 degrees C. Okay, so that's been running for about 6 minutes, sorry, about 5 minutes, and it's reached equilibrium. So just to explain that, as the temperature on this plate is rising, there's a temperature sensor underneath it. As it's rising, it's in a linear fashion for every degree C of increase, it's increasing the RPMs of the fan. So clearly, and the fan, therefore, the faster the fan's going, the more air movement there is around the fins of the heatsink. And as a result, the heat is dissipated more efficiently. So running from cold, now what's happening here? There's about 12 watts, as you can see from the power supply here, there's about 12 watts being dissipated into the load, and there's about 29 watts being dissipated in the actual regulator circuit. So that's kind of what it looks like currently. And reaching that point of equilibrium, we can sit there and wait all day. It's not going to get any warmer, obviously. So what I'm going to do now is I'm going to stall the fan, and then I'm going to let the now. Fortunately, these fans protect themselves, so it's quite safe to stall them. They'll actually stall, sense the current, stop running, and then try about every 5 seconds to restart. I'll just jam the pen in there so they can't. And I'm going to let it on its own without any air cooling warm up to 50 degrees C, and what you should see is this now climb. So you can see the mark space ratio, by the way, at this point, at this equilibrium point with dissipating 30 watts, we're only about 45%, about 46 or 47% maybe of the rated fan's speed, so it can run over twice as fast as it's currently running, and the RPMs are currently about 1750 revs per minute. So I'm going to stall the fan now and then let it warm up. Again, I'll speed up in editing so you don't have to sit through the pain, but you will see the thing increase, and once it's reached 100%, you'll see it'll effectively stop pulsing. It'll just be a permanently high, which is trying to drive the fan on full. And then I'll come back and talk to you briefly, and then I'll let it find its equilibrium, coming back down the other way by self-cooling. Okay, so let me just stop the fan. I'll just drop that pen in there to stop it from starting. Okay, and we'll watch that and let that heat up. Okay, so we can see we're up at 50.6 degrees, 50.7 degrees. It's just on its way up. The PWM output on the microcontroller that's driving the fan is now gone to full on, so it's expecting that fan to be running at full pelt. So what I'm going to do now is let the fan run under its own steam. I'm going to leave the load in place. It's still dissipating 30 watts in the heater. We're up to 51 degrees now, 52 degrees. By the way, with that thermal mass there, it took a little over 4 minutes to get from where it was, which was 36 degrees, up to 52 degrees with 30 watts being dissipated into the load. So really quite good. You know, the thermal properties of this thing are actually pretty decent. Anyway, I'm going to start that running again, and you should see now as soon as it starts to have an impact. So we're at 53 degrees right now. As soon as it drops below 50, you'll start to see the PWM kick in again, and it'll start to regulate the fan speed down again, linear in direct proportion to the temperature of the heatsink. So that's quite warm. That's quite hot to touch now. That's like it feels like putting your hands around a hot cup of tea or coffee. And there you go. It's just kicked in there now, and it's starting to cool down already. So I'll leave that run now, and then I'll come back once it's reached its equilibrium again. Okay, so that was just enough time for me to make a cup of tea myself. The temperature is down to 36 degrees, which is about its equilibrium point again, around about 46%, 47% drive. So there we go. So as far as the thermal management is concerned, I thought I was going to have to do something a bit more sophisticated than that. I was thinking about sensing the power dissipated in the regulator, and based on that being high, or the amount of power being dissipated, that I would artificially increase the speed of the fan early on to help dissipate the heat. When I do that final test under full load, I will have a look at that, and maybe have to do that. But right now, the simplicity of the way it works at the moment is perfectly fine as far as I'm concerned. The thermals are actually quite efficient. These are CPU coolers, and this is a good quality one. This is the one with the copper core that I showed you. Are actually very good. So yeah, as far as I'm concerned, that's it. The thermal management is done. Okay, so the next thing I have to do here is start measuring the load and doing some measurements. Now the problem I've got with that is I have this dummy load here which I have to learn how to use. So I'm probably going to finish up with this article here, because this part 12, because there's enough content in there already, and then I'll go away and do a bit of learning and start to think about setting up to specifically to spec this and to look at some of the characteristics of it. See how good, bad or indifferent it is. Okay, so if you found this useful, please give it a thumbs up. If you've got any comments, please leave comments. Happy to answer them if I have time. And I'll see you on the next instalment. Thanks very much for watching. With the latest firmware upgrade, I've also modified the software, really just to add some additional parameters so I can monitor what's going on. So there's nothing really new here that you wouldn't expect to see. So when built the final version, the version that you've just seen, I have now added a monitor for the pre-regulator voltage. So we can see the pre-regulator voltage here is running currently at 17.5 volts. That's what the DC voltage it can see. And this is not using the precision ADC. This is just using the onboard ADC, the microcontroller's onboard ADC. So it only has to be approximate because we're using it to measure power. Also, you can see we're measuring the temperature of the heatsink, so it's currently sitting at 21.4 degrees. We're calculating the regulator's power. That is the power that's being dissipated in the regulator at any given point in time. And we're also calculating in the microcontroller the power that's being delivered into the load, and we're also sensing the speed of the fan. Now, I did state previously that I'd remove the line frequency sense, which I've now put back, and there's a reason for that. The analog to digital converter has an option, an input pin to control whether or not the filter, the integral filter, is filters out 50 cycles or 60 cycles. That's obviously for the European stroke US market. So what I'm actually doing there, I'm sensing the line frequency, and depending on whether the line frequency is running at 50 or 60 cycles, I'm putting the ADC in the right mode, and all that does is just helps lower the noise, just to get more accurate readings anyway. So that's what's going there. So we can see the fans running at 1620. If you watch this, how I'm also displaying it here. I've added these 3 additional displays here. So if you watch the fan, I'm just going to slow it down with my finger, and as I
as I slow it down, you can see it sense, and I can slow that right down to stalling. I can turn it, yeah, and let it spin back up. If I've set the voltage to 4 volts, I've set the amps to 4 amps. I'm driving into a pair of those halogen lamps in parallel. If I switch the output on, you can see the volts. I'm delivering 4 volts, drawing 3.14 amps. You can see the filament warming up. Simple multiplication there gives me the power that's being dissipated into the load. More importantly, it's calculating the power that's being dissipated into the regulator. Now, the reason why that's jumping up and down is obviously it's looking at the pre-side of the regulator, and that's effectively a kind of sawtooth waveform, because on the input side of the regulator, of course, you'll have the ripple of the smoothing capacitors. So that's why it's jumping up and down. I've not tried to do too much of it because it's just not that important. It's just it's important to know approximately how much power is being dissipated into the regulator, and no more. Everything else is as you've seen it before. So that's really it. I'll finish up here. And again, if you're enjoying the project, or you like this particular segment, please give it a thumbs up, and I'll see you next time. Thanks.